In this video, we're going to discuss how to complete the square in order to solve for x. There are various reasons to complete the square. Not all of them involve solving for x. For example, when we study conic sections, we'll complete the square in order to find the center of a circle or a hyperbola or an ellipse. Let's take a look at what a problem might look like where you might need to complete the square in order to solve for x. On the left side, you'll see the standard equation for a quadratic formula or a quadratic equation set equal to 0. When we write it in this form and the variables are in order by the power on the variable x, where x squared comes first, then the x term, then the constant, then we refer to their coefficients as a, b, and c for the constant. A is always attached to the x squared term. B is the constant multiplied by the x, but does not include the x, and c is the constant. When we look at this equation here, we can see that this is a quadratic equation in standard form. We have 2x squared plus 8x plus 11 equals 0. In this format, all of the terms are on the left, 0 is on the right, and we have it written with the x squared term first, the x term second, and the constant third. In this case, our a is 2, our b is the coefficient of the x term, or 8, and our constant is a positive 11. In order to know what a, b, and c are, you need to first have everything on one side of the equation in descending order by the power on the variable x. Once we have that, we can complete the square. I'm going to complete the square on both the standard equation with ax squared plus bx plus c, and on our example, 2x squared plus 8x plus 11, so that you can see how the two formulas match up and where the quadratic formula is coming from. The first thing we need to do is realize what our goal is. When we get to the bottom, we are hoping to have x inside parentheses added or subtracted to a constant and the entire parentheses squared. Then we'll be able to apply the square root property in order to solve and isolate x. Let's get started. To get started, the first thing we need to do is remove the a from the x squared term. You will want to check first to make sure that your quadratic equation does not factor. If it factors, factoring is always an easier way to solve the problem. It will still work by completing the square. In fact, completing the square always works, but it is never the easiest way to solve a problem. So first check to make sure it will not be solved by factoring, and if not, then completing the square is a good option. To do that, I need to remove the 2 from the x squared, but I also need to factor it off the x term. So I'm going to move the 2 here. I'm going to open parentheses, and this becomes basically a form of division. I'm factoring the 2 out. So what that gives me is actually the 2x squared I originally had divided by 2. The 8x that I originally had divided by 2. And then I'm going to close this. The constant is not included in the completing the square part. It is pushed off to the side and out of the way. It's still there, it's just not used for completing the square. Now we'll simplify what's in here. The 2 divided by 2 leaves me with x squared. The 8x divided by 2 leaves me with 4x. Leave some space because you're going to add something inside the parentheses, then plus 11 equals 0. You may find it easy to go from here down to here and skip this step in the middle, and that's fine. If we repeat the same steps over here on our standard formula, then I will have to factor the a out of the ax squared by dividing by a, and out of the bx by dividing by a. I don't do anything with the constant term. It is not a part of completing the square. When I reduce and simplify the left side here, then I will get a times x squared plus b divided by a times x plus c outside the parentheses equal to 0. You'll notice that now inside the parentheses, the coefficient of the x squared term is positive 1. This is exactly what we need in order to complete the square. You'll also notice that the coefficient of the x term, after removing the a and putting it to the outside of the parentheses, the coefficient is b divided by a, or in this example, 8 divided by 2, which gave us 4. So when you're completing the square, the first thing you want to find, and you may want to write this down at the bottom, is b divided by a. In this first example, it was 8 divided by 2, which gives us 4. This is another easy way to move from this first step straight to this step. You know the 2 has to be removed from x squared. The coefficient left on the x will be the original b, coefficient of x, divided by a, original coefficient of x squared. What's the next step in the process? The next step in the process is to force this equation to become a perfect square trinomial, even though it is not originally a perfect square trinomial. A perfect square trinomial, when factored, will be the same two binomials multiplied together. In order to do that, I've got to find exactly the right number so that when this trinomial is factored, it will factor as the same two binomials multiplied together. To do that, I'm going to take this number I found down here, which was b over a. I will take the b over a and perform two steps that will be needed to find the perfect number to add to the trinomial so it will factor perfectly. First, I take half of the number I got for the first step. So I take 1/2 times b divided by a, which in my example is 1/2 of 4, which is the number 2. Then I take that number and I have to square it. That means I'm taking half of this b over a and I'm squaring the whole thing, which becomes the 2 that I got in line 2 squared, or 4. This 4, the third value that I got in these steps, becomes the third number that I have to add and subtract in these parentheses. I'm going to write this in a different color so that hopefully you can see where it comes from. This 4, ringed in red, which I hope will show up, you're going to add and subtract inside the parentheses. Now, why do I need to add and subtract the number? I was trying to force it to be a perfect square trinomial, which is basically the first 3 terms, the one with the plus, not the one with the minus. However, I can't change the problem, and originally there was no plus 4 here. So to compensate, I add 4 and subtract 4. We call this adding 0. By adding 0, I've changed the way the equation looks, but I haven't actually changed the solutions to it. Now, the first 3 terms will factor as a perfect trinomial into a binomial squared. This means that this part becomes x plus 2 times x plus 2, or x plus 2 quantity squared. Now what happened with the a that was at the front? It's still there, which means I still have to have the 2 here and the 2 here. What happens with the minus 4 that I put in to compensate for the plus 4? The minus 4 did not get included in what got factored, which means I need to distribute the 2 that's outside over the minus 4 and bounce it out of that parentheses using the distributive property. This becomes 2, my original a, times the negative 4 that I had to use to compensate for adding 4, plus the 11 that was originally there, equal to 0. Now, notice something else that's kind of unique and special. Down here in that second line, I got a value of 2, and the number that showed up, including the sign inside that binomial, was plus 2. This always works. You will always get exactly this number inside the binomial square, including the sign. You don't actually have to factor the trinomial. It must end up with the number from row 2. This comes from adding and subtracting the number in row 3 to form the perfect square trinomial. The minus part, to compensate, gets bounced out of the parentheses, multiplied by the 2, and then we include the constant, which has been there all along. Let's complete the problem. The 2 times negative 4 would give me minus 8 plus 11 equals 0. Now we have 2 times the parentheses, x plus 2, the quantity squared, negative 8 plus 11 gives us 3, equals 0. At this point, you can see we have completed the square. In order to solve for x, we have to isolate x. But to isolate x, we have to first isolate the perfect square. That means we would move the 3 to the opposite sign of the equals. We would move it by subtracting 3 from both sides of the equation. That would leave us 2 parentheses x plus 2 quantity squared equals negative 3. Next, we would divide both sides by 2, and this will give us the perfect square isolated. At this point, we would take the square root of both sides. Unfortunately, we don't know anything about x. We don't know if it's positive or negative. We don't know if when we add 2 to it, it's positive or negative. Because it could be either way, we will have to include a plus or minus on the other side. So this becomes the square root of x plus 2 squared equal to plus or minus the square root of 3/2. To finish this, this gives us x plus 2 equals plus or minus the square root of 3/2. To complete the problem, I simply need to subtract 2 from both sides. Now, I do have a negative under that radical, which means that this is a complex solution with an imaginary part. My final solution to this problem would be x equal negative 2 plus or minus I square root of 3 all divided by the square root of 2. If you want to rationalize the denominator, you would multiply this by radical 2 over radical 2, which is a form of 1. This would leave us x equals negative 2 plus or minus I square roots of 6 from 3 times 2, all divided by 2. This is our solution for what values of x would solve that quadratic equation. Let's repeat these steps now on the original problem. First step again is to factor the a off of the x squared and the x term by dividing it out of those two terms. That leaves us with the coefficient of x being b over a. This is line 1 in your scratch area. The next step, to force it to be a perfect square, is to take half of b over a and square that value. If I don't have actual numbers, I'm going to end up with 1/2 times b over a quantity squared, which would be b over 2a quantity squared, which is the same as b squared over 4a squared, which means up here I need to add and subtract that b squared over 4a squared. So my next line is going to be x squared plus b over ax plus b squared over 4a squared. Then I have to subtract to compensate. Since I cannot change the problem, it has to still be equivalent to what I started with. The first 3 terms with the plus will become a perfect binomial squared. The number inside the binomial will come from the second line, which is my 1/2 of b over a, or b over 2a, which means this becomes x plus b over 2a quantity squared. Now I have to bounce out the minus part that I used to compensate, and this has to come out for the next part. So this becomes plus a times negative b squared over 4a squared. Then I have plus c equals 0 still. To finish completing this part, I need to clean up some of the algebra a little bit. I can think of the a as a over 1, and that a will cancel one of the a squareds and leave me a in the denominator. This gives me a times x plus b over 2a quantity squared. I can say positive times negative is negative. So I have a negative or a minus b squared over 4a, and then I've got a plus c equals 0. In order to solve for x, I need to isolate the x. But to isolate x, first I have to isolate the binomial squared. So my next step is to move these two terms to the right side of the equation. Let's do this on a fresh sheet. I have recopied the problem on a fresh sheet. Let's isolate the binomial square and solve for x. First step is to add b squared over 4a to both sides of the equal sign and to subtract the c. This leads me to the next line, which is a times the quantity x plus b over 2a all squared. Now on this side, I have b squared divided by 4a minus c. It would be helpful to get a common denominator so I can combine these two terms into one fraction. The common denominator will have to be the only denominator I have on the right, which is 4a. In order to do that, I need to multiply the c by a over a and 4 over 4, or by 4a divided by 4a. This will give me b squared over 4a minus 4ac over 4a, And now that the denominators are the same, I can combine them into one fraction, b squared minus 4ac divided by 4a. Now b squared minus 4ac should sound familiar to you. It comes from the quadratic formula. Let's continue the problem by solving for the binomial square. In order to get the binomial square by itself, I need to divide by the a. To divide by a is the same as multiplying by its reciprocal, 1 over a. So on the left, I can think of it as divide by a, and on the right, I can think of it as multiply by the reciprocal, 1 divided by a. This gives me, on the left, the binomial by itself, still squared, and on the right, b squared minus 4ac still in the numerator over 4a squared now, because a times a gives me a squared. I've isolated the square. Now I take the square root of both sides. I don't know anything about the sign of what's in the parentheses, which means that I will have to include a plus or minus on the side without the variable. This gives me x plus b over 2a quantity squared under the radical equal plus or minus the square root of b squared minus 4ac divided by 4a squared. Now in this case, when we have this square root here, I can split it between the numerator and denominator, because you can split radicals between things that are divided or multiplied. I cannot split across the subtraction, so I won't be able to do anything about the numerator, but I can at least split it into two parts for the denominator. This gives me plus or minus the square root of b squared minus 4ac, all divided by the square root of 4a squared. The square root of 4a squared becomes 2 absolute value of a. This becomes b squared minus 4ac over 2 absolute value of a. Now, the absolute value of a is either a or negative a, depending on if a is positive or negative. But because the plus or minus will include all sign combinations, which lets me drop the absolute values and simply write plus or minus b squared minus 4ac divided by 2a. Normally, I would need the absolute values, but the plus or minus gives me both anyway. Now, on the left, all the radical does is remove the square. It does nothing to what's underneath it. So I still have x plus b divided by 2a. Now, in order to solve for x, I need to subtract the b over 2a from both sides. When I subtract the b over 2a from both sides of the equation, I get x equals negative b over 2a plus or minus the square root of b squared minus 4ac, all divided by 2a. And since they have a common denominator, you can also write this as negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. That's right, completing the square on the standard form ax squared plus bx plus c is, in fact, the quadratic formula. That's why both of these methods work in all cases. They are the flip side of the same coin. They are, in fact, the same technique. Let's do another example of completing the square. Here's our next example. Let's look at 3x squared minus 6x minus 20 equals 0. It is possible to take the 3 out of the 3x squared and the 6x, but not the 20. It's possible to take a 2 out of the 20 and the 6x, but not the 3x squared. There's no greatest common factor, and 3x squared minus 6x minus 20 does not factor. We're going to complete the square. Let's recall the steps. Step 1, remove a from x squared and x by dividing both terms by a. Recall that a is always the coefficient of the x squared term, but without the x squared. That b is always the coefficient of the x term, without the x term, and c, of course, is the constant. This requires that the equation be written in standard form. Everything on one side, 0 on the other side. Now let's get started. If I factor out the 3, this is going to leave me with 3x squared over 3 minus 6x over 3, and the minus 20 is off to the side. This simplifies to x squared minus 2x, leave some space, minus 20 equals 0. In other words, the first thing I need to compute is b divided by a, which is negative 6 divided by 3, which is negative 2. That number will be the number that shows up after you've removed a from the x squared and x term. Step 2, we need to find the perfect number to add so that the first 3 terms will factor as a perfect square trinomial. So we take half of the number we just got, which is 1/2 of a negative 2, which is a negative 1, and then I square that number. When I take the negative 1 and I square it, I get positive 1. The third number becomes the third number in the trinomial. I need to add 1 so that it becomes a perfect square trinomial. However, I've added a number that wasn't originally there. To compensate, I subtract 1. The first 3 numbers become the perfect square trinomial, which will always factor as x with the middle number inside with it. Since this is negative 1, it will be x minus 1, quantity squared. The 3 on the outside has to multiply by the unused compensating minus 1 and bounce out. This becomes 3 times negative 1 minus 20 equals 0. Multiplying out and combining with the minus 20 give us the next 2 lines. At this point, we have completed the square. What's left to do is to solve for x. To solve for x, we need to isolate x by first isolating the binomial square. We'll move the 23 first by adding the 23 to both sides of the equation, and that will give us 3 times the quantity x minus 1 squared equals 23. Next step, divide both sides by the 3 to isolate the binomial square. And this will lead us to x minus 1, quantity squared, equals 23 divided by 3. Now we take the square root of the binomial squared, which lifts off the square, and we just get x minus 1. On the right, because we don't know if x minus 1 ended up positive or negative, we have to include the possibility of either one. And this becomes 23 over 3. If you want to rationalize the denominator, you will need to split it into 2 parts, square root of 23 over square root of 3. I personally do not care if you rationalize the denominator, and I will not require it. Some professors prefer it, but I'm not one of them. So our next step will have us isolate x by moving the -1 to the other side. This becomes +1, +1, and I finally get x equals 1 plus or minus the square root of 23 divided by 3. This answer is just fine for me. If you want to rationalize, you will need to multiply by radical 3 divided by radical 3. Let's take a look at one more example. Here's another example. 2x squared plus 5x minus 41. Again, 2, 5, and 41 are all prime numbers, so there's nothing that can be factored out, and that does not factor by ordinary means. In this case, we have no choice but to use the quadratic formula or complete the square. This problem is going to be quite a bit more difficult than some of the others we've done because it's going to involve fractions from the get-go. Just be careful, use lots of paper, and leave lots of space. It does help. First thing we need to do is remove the a. To do that, we need to find b divided by a. We're going to take a shortcut and just do it by looking. b is 5, a is 2. This gives me 5 divided by 2. That means that when I rewrite this, this should be x squared, same sign, so plus 5 divided by 2x, leave some space, minus 41 equals 0. Now this is going to be more difficult because our coefficient of x is now a fraction. We still do the same steps. Take half of that number, which is 1/2 of our 5/2. Remember to multiply straight across with fractions, so we get 5 over 4. Take that number and square it. The 1/2 of b over a is squared to get the third number, which goes in the third place, the perfect square trinomial part. So this gives us 5/4 quantity squared, which is 25 over 16. Yes, it's nasty, but we're stuck with it. So we add 25 divided by 16, and we compensate for that by subtracting 25 divided by 16. The first 3 terms become the binomial square. What goes inside the binomial is the x and then the second number with the same sign. So it becomes x plus 5 over 4 quantity squared. The number that didn't get used has to bounce out and show up next. So I get plus 2 times negative 25 over 16 minus 41 equals 0. At this point, this part is good, but I need to simplify this part. In order to do that, I can think of the 2 as 2 over 1 and do some simplification before multiplying it out. This leads me to minus 25 over 8. In order to combine it with the 41, I need a common denominator, which will have to be 8. I can think of 41 as 41 over 1 and multiply by 8 over 8. This will give me 328 for the numerator divided by 8 equals 0. The front part is unchanged. Now we'll combine these two terms, and this will give us a negative 353 divided by 8 equals 0. The next step is to isolate the binomial square by moving this to the other side of the equal sign. So we add the fraction to both sides to move it. And this leads us to 2 times the quantity x plus 5 over 4 squared equals 353 divided by 8. Next, we have to get rid of the 2 by dividing both sides by 2. We can also think of this as multiplying by the reciprocal of 2, which is 1/2. On the right side, I will think of it in that way and multiply by 1/2. 353 is not an even number, so I can multiply the 8 and the 2, and that will give me 353 divided by 16. This isolates the binomial square on the left. Next step, take the square root of both sides. The side without the variable will get a plus or minus, and so I get plus or minus the square root of 353 divided by 16. On the left, I get x plus 5 over 4. Now, I can split this into 2 pieces, and I would in this case, because I know that 16 is a perfect square. This lets me evaluate the square root of 16 while the 353 stays under the radical. This becomes plus or minus the square root of 353 divided by 4. To complete the solution, we will subtract the 5 over 4 from both sides of the equation and write the final answer as negative 5 over 4 plus or minus the square root of 353 divided by 4. Since these have a common denominator, you could write them in one combined form if you prefer. Let's look at one final example before we close the video. This final example is somewhat different in that the coefficient of the x squared term is negative. How is this going to affect our process? And the answer is not at all. It's going to proceed exactly the same way it has before. Let's see how this works. To make it a little bit easier, we are going to write out a, b, and c for this example. A is the coefficient, or the number multiplied by x squared. Though not fully written, it is a negative 1. B is the coefficient of the x term, but does not include the variable, so it is 3. C, of course, is not as useful, but it is minus 15. Now, for the next step, we need to take the a off of the x squared and the x term. That means we need to find b divided by a, which gives me 3 divided by negative 1, which is a negative 3. This will rewrite our problem as negative 1 positive x squared, since the negative has been removed, but it changes the sign of the x term from plus 3x to minus 3x. The minus 15 is unaffected by that because I did not remove a from c, only from the x squared and the x term. Next step is to find the number to add to make it factor as a perfect binomial squared. That means take half of b over a, which is 1/2 of our negative 3, which is a negative 3 over 2. In order to finish it, we need to square that. So I take half of b over a and I square it, which is negative 3/2 squared, which becomes a positive 9 divided by 4. In here, I need to add 9 divided by 4, and to compensate, I need to take out the 9 divided by 4. The first 3 become my perfect binomial square of x minus 3/2, quantity squared, same number here as in the second step. And then this part has not been used, so I have to multiply it by the original a and bounce it out of the parentheses using the distributive property. This means I have minus 1 instead of plus, because my a is negative, times negative 9 over 4. I'm simply distributing, and then I'm bouncing it out. And then the minus 15 is still there. The next step is to clean up the latter two parts, which will always be constants, and to get a common denominator. Since a double negative will make this positive, this will give me a plus 9 over 4, which means I need to rewrite 15 in terms of fourths by multiplying by 4 over 4. That would give me minus 60 divided by 4 equals 0. And that would leave me with negative 1 times x minus 3 halves the quantity squared. Negative 64 plus 9 fourths is a negative 51 over 4 equal to 0. Now we isolate the square by first moving the negative 51 over 4 and then getting rid of the coefficient. So first we add 51 over 4 to both sides, and this will give me negative 1 times x minus 3 halves quantity squared equals 51 divided by 4. Now I've got the negative here. I can either divide by the negative, or since it's just a negative 1, I can also multiply by the negative. Either way works. You can think of it either way. In this case, I'm going to think of it as multiplying by negative 1, and that will make this x minus 3 halves the quantity squared equal negative 51 divided by 4. The negative means when I take the square root, I am going to have an I, which means this is a strictly complex number with an imaginary part. Now I take the square root of both sides. The side without the variable x will have to have a plus or minus in front. And since I know that 4 is a perfect square, I'm going to split the radical up into two pieces from the beginning. That will give me the negative coming out as I, 51 still underneath, and then I've got the square root of 4 is 2. Now, does 51 factor? It's not even, so it's not divisible by 2, but it is divisible by 3. However, it is 3 times 17. And 3 times 17 does not give me a pair of factors, so it will remain wholly underneath the radical. On the left, I just get x minus 3 halves. To complete the solution for x, I need to add the 3 halves to both sides. This will give me x equals 3 halves plus or minus I square roots of 51 divided by 2. This is precisely the same solution you would get from applying the quadratic formula. I hope that this helps you to complete the square in order to solve for x, and this completes the video.